Okay. Uh, so, uh, Starting where we left yesterday, uh, we basically quickly reviewed the coordinate system, the forces, and the moments acting on the aeroplane, and maybe reminded ourselves of something like the static margin and that the position of the CG is always changing, but as long as it's in or within a safe zone, it's okay. We can still fly. The characteristics of the flight will change with the change of the CG position, but it will not really become catastrophic. Okay, I will just need to start by the lift of the whole airplane, but because we may come from different backgrounds, or maybe the previous professor was using a different way of approaching stuff. I'll try to quickly again review things that we already know about lift in order to be able to build on them and do some calculations for the whole aeroplane. So this is what we'll try to do today, inshallah, and it will probably extend to next week to cover more of what you already know, but to collect it together. Okay? So, generally speaking, when air flows or any fluid flows on anybody, any given body, forces start to be created due to the changes that happen in pressure on one hand, and on the other hand, some of them are created because of viscosity. In many cases, we just ignore viscosity because it's quite low in air. But probably you already know that without viscosity, we wouldn't have been able to fly. Okay, yes, ignoring it in the calculations, but assuming that it still exists is kind of a dilemma. But engineers use these things all the time. Salam alaikum. Hmm? Okay, it should be 14 here, yeah. No problem, no problem. Come in. Okay, so let's just imagine that you're trying to put your hand outside a moving car. I'm not sure whether the law allows this or not, but even if it doesn't allow it, as a human being, you have the right to try it. Okay? It's a very nice experience that most of us had it, whether as children or as adults. Until today, I like it very much to get my hand outside the window and play around with moving my hand in the air. What happens is that as the air passes around your hand, it starts pushing on some parts more than others. Okay, when it pushes on these parts, that's what we call increase in pressure, right? You probably already know that on the other parts, the velocity increases, and due to Bernoulli equations, pressure decreases, and thus, quote unquote, a negative change in pressure occurs. Adding these up, a positive increase from one side and the negative increase on the other side add up to a total force. Okay? The fundamental force actually for any flow of fluid on anybody is drag. Okay? This is sad for us. We hate drag usually, all the time. Okay? But whenever you move, there is anybody moving in any fluid, drag is created. Is it associated with lift? Doesn't have to be. Okay, so drag is the fundamental force. We cannot get rid of it. Drag is basically defined in many ways, but the one that we care for in whatever is related to flight and aerodynamics is the force that's parallel to the airflow and in the direction of the airflow. So if it's in the direction of the airflow, it's against the direction of the motion of the body, right? And that's what pushes your hand if you're putting it in completely against the airflow. It pushes your hand backwards. Okay, this is what resists the spoon while you're trying to mix some sugar with your tea or coffee, right? That's against the flow. Okay. The other force which we always pray to have as much of as possible is lift, because lift is what's responsible for flight. Without lift, there is no flight. The definition of lift, as per what Sir George Cayley defined in 1799, was that it's the resultant of the force normal or perpendicular to the air flow. Okay? This is what we are seeking all the time. So, and that's what's used to raise or pull the body against gravity. Well, does it always pull it against gravity? You may want to create negative lift, right? But generally speaking, when we say lift, it's supposed to be upwards, right? Okay. Negative lift exists. Yes, negative lift is useful. Believe it or not, yes. Okay, and as we will see, inshallah, in detail, sometimes we deliberately use it to create negative lift. Okay, okay, so the wing, on the other hand, is any body that's designed with the purpose of mainly creating lift. Of course, for generalization, we can assume that anything moving in any fluid can be called a wing. But this is too broad of a definition that's not useful for us. When we say wing, we are talking about some geometry that's usually slender, thin, and tall, okay? And this, its length, its main length, which we call the span, is usually perpendicular to the direction of flight. Okay? So if I'm raising my hands like that, it's probably meaning that I'm moving in this direction, I'm flying in this direction. That's a very specific and narrow definition, but useful for us. Okay? Okay. A wing's cross section, any cross section of a wing can be called an airfoil. Though most of the airfoils that we know and use usually have something that looks more or less like what's displayed on the monitor. Okay? This is again a narrow view of an airfoil because for example, if we're talking about supersonic flight, you probably did you study supersonic flow? Yes. Okay. Many of the supersonic airfoils are in a diamond shape, right? But for subsonic flow, which is most of the aircraft, a diamond shape is not really that good. We need something grounded from the front and pointed from the back. Okay? Nevertheless, the broadest definition is any wing cross section can be called an airfoil. Okay? Okay. This is a neat, I call neat, drawing of an airfoil. Okay? That was generated by Python. So you probably can get this code. It's very easy code. I can either give it to you or you can get it from ChatGPT. Okay, to draw an airfoil. Given the four-digit nomination of the airfoil, you can get the airfoil right away. There are a lot of uh, software packages, small ones, that are very useful when analyzing airfoils. Probably the one that I love, I've been using for ages now, Java Foil. Okay, although sometimes it's hard to get it running, but as soon as it gets running, it's very nice in analyzing 2D and 3D wings. Okay, if you can get it on your computer, يعني it would be a very nice tool. Uh, I will not be repeating here what you already know about airfoils, but let me just stop here and focus on one thing. It's the maximum lift. Okay, the maximum lift of an airfoil is something that always is associated with any airfoil. As you increase the angle of attack, you increase the coefficient of lift, but up to a limit. When you reach that limit, the coefficient of lift starts dropping. Uh, Practice and computational fluid dynamics says that it will not be dropping forever. It will grow up again at a higher angle of attack. But that's useful for severe maneuvers for fighter aircraft. Most of our work will be focused on regular flight, which is either small aircraft or commercial aircraft. Okay. However, this is important to know for any wing in order to recognize how much lift that given wing can produce. Without knowing that, you can reduce your speed forever. Remember in the previous course, aircraft mechanics. It was called aircraft mechanics. Hmm? Flight mechanics, okay. In the flight mechanics course, you learned about V minimum, the minimum speed you can fly at. How would you identify it? By getting the maximum lift coefficient and the weight, and by that you can find what is the value of my minimum speed. Okay, below which would the aeroplane fall? Okay, stalling. That's a very big word. The minimum is like depends. The regulations specify minimum speed. No, 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 forget the regulations. I'm flying my own remote controlled aeroplane. The amount of lift it's produced is not enough to like counteract the weight of the aircraft. Okay, and so what will happen? The V minimum is the least loss you can fly before. Yes. Yeah. But what in this case? How would you define stalling? Stalling is a very broad word, by the way. It can be applied on so many things. But now I am a crazy pilot. I'm flying my own Cessna, okay, and its minimum speed is 30 meters per second, okay, and I decided to fly at 25. Hmm? I cannot hear multiple sources. So who's talking? Less thrust. Less thrust? Because you have less speed, you have less thrust. I decided to change the speed, whether by thrust or by whatever. What will happen to my aeroplane? First of all, the loss of the speed will first of all decrease the lift and goes lower enough because the stall, which is separation of the airflow of the. You're too much of an engineer, huh? Hmm? That's that. All what will happen is you lose altitude, but you will not fall. Okay? We were raised as engineers, as aerospace engineers, to be totally afraid of the zombie called Stoll, right? But just think about it for a second here. I am flying at a speed less than the minimum speed. So what will happen? I will not just fall like a stone, right? It just means that the total lift I'm producing by my airplane is less than the weight, right? If it's less than the weight, what will happen? I will start losing altitude. I'm not falling, right? I'm not falling, I'm just landing, baby. Although it's not a good idea to land at your stall angle of attack, okay? But I'm still flying, right? Remember that, okay? Okay. Again, let's quickly review now, go from airfoil to the cross section to what we call a 3D wing. Okay, a finite wing is what we already use for flight anyway. Okay, what happens with a finite wing? One thing that causes a lot of changes, which is the wingtip vortices, right? It reduces the amount of lift produced by the wing. It creates a change in the effective angle of attack. Okay, it produces wakes that create downwash and upwash. Okay, which affect everything that's flying behind the wing. Okay, and it's powerful enough to hurt someone, or even to, if it's a 747 and you are very unlucky to get in the wake of a 747, even if you're riding a bus, the whole bus will go around and it's not going to be a very nice experience. That's why I would suggest that you do not fight the bad guys on the wing of a 747 while it's taking off. Okay? Tell Bruce Willis that, please, because I want to meet him just to tell him don't do that again. Okay? Okay. Just I like always, whenever mentioning finite wings, I like to stop at this picture. What's happening here? These are geese or some sort of bird. Okay? I believe they are called geese. But anyway, uh, why are they flying in such a formation? What regarding wakes? Mm. They will not be in the wake. Okay. Any other ideas? Hmm? What will create less drag? If there is no effect of the front one, there will be. So he's removing the air. He's not. Just think about it a little bit more. You're on the right track, by the way. I like making jokes. Okay? You're on the right track, but you got something missing. Ah, something related to that. The? How would it do that? Okay. Okay. Look at this wake. What's happening here? High pressure at the low surface, right? Pushes the head this way and starts rotating, right? It's always rotating this way, right? Right? Okay. Now, Fatima and Muskan. Muskan. Okay, Muskan. Fatima and Muskan are now exactly behind the wing, okay? And they are behind, so I'm flying this way, okay? The wakes are. So, what do Fatima and Muskan see from the wake? Hmm? Are you? Right? You are in the downwash zone. Okay? Right? So you're always seeing an effect of air going down added to the normal flow. But Yusuf, upwash, upwash. That's not a word that we use a lot, right? But it is there, isn't it? For it to rotate, part of the air is going up, and the other part is going down, right? So this guy is seeing the air in a different way. His addition is upwards, not downwards, right? So if the air is going up and he weighs, don't tell them the weight, you weigh, let's say 60 kilograms, okay? Would he need to fly with a lift that's equal to 60 or more or less? Less lift, right? So these are smart geese, aren't they? Because they're flying in the upwash. So the air generated by the front goose, okay, helps these waves help the ones in the back to fly with less effort. They need to produce less lift, right? Because the air is going up, not down. Okay? So they're still in the effect of the wave. They didn't lose the effect of the wave. They are using the effect of the wave. Okay? Got it? That's why I'm telling you, you were on the right track, but missed the turn. I mentioned that they use the word but I don't know how. It didn't lose it. No, it's using. You said lose or use? I said use, but I don't know how. Okay? So actually this guy is carrying himself. Right? He's on his own. But his byproducts of aerodynamics, okay, usually bad byproducts, bad for the environment, okay, usually they are positively used by the two right behind them, okay, to fly easy. And the other two in the back are using the upflow generated from the guys in front of them. Okay? That's why it is common practice for birds that fly long distances to rotate the position of the lead. Okay? The leader goes backwards, after a while, someone else goes to the front to help the others. Okay? Okay. So, yes, we can use it. Okay. Well, just a reminder, For the wing itself, it's affected by parts of the downwash. That's why the effective angle of attack changes, changing the direction of flow, which reflects for us as two things: a reduction in the lift and creation of what we call induced drag. Right? Okay. Well, I will not spend much time now talking about winglets. You probably know the general idea. Winglets basically reduce the effect of the wingtip vortex. Okay, so it increases the efficiency of the wing and reduces the effect backwards as well on the tail. Now, we quickly reviewed what you already know about airfoils and finite wings. Okay, let's jump to the whole configuration, and for that I'll need to start writing or drawing, and you'll get to get acquainted with my bad handwriting. Okay. uh, okay, there we go. Bismillah. Now we have a whole aeroplane configuration with a wing and a wing, right? A big wing and a smaller wing. We usually call them the wing and the tail, or the wing and the horizontal stabilizer, but for aerodynamics, they are both wings. Okay. Uh, I will start by something that's not always done when studying flight dynamics, but I'll just start by talking about the lift generated by the whole aeroplane. And I'll just say, here we are. Okay, so there for the aeroplane, for the whole aeroplane, L total, which I will refer to as L from now on. Okay, total lift of the aeroplane. I can say that it's generated by the lift of the wing plus the lift of the tail and maybe plus the lift of the fuselage. Can the fuselage produce lift? It can. Okay, usually quite small compared to the wing and tail, but it can be large enough to use it for flight. Okay, you have probably heard before about wingless aeroplanes or flying, or lifting body aeroplanes. Okay, so, but for our case, we will just ignore this for now. Okay? Okay. The lift of the whole aeroplane is usually known as, or written as, Q infinity SCL, where this is the dynamic pressure equal half rho infinity V infinity squared, right? And this is the reference area. Right? For the airplane, the reference area is usually the wing area. That's by choice. Okay? And the most important part probably is the lift coefficient, right? Which is, again, some combination of the lift coefficient of the wing and the lift coefficient of the tail, right? But again, it can be generally presented as CL equals CL naught plus CL alpha alpha, where alpha is the angle of attack measured from the body reference axis, the body reference axis and the airflow direction, right? Okay. Similarly, the lift of the wing may be written as infinity S wing CL wing. Do you agree? Okay. Which can be written as Q infinity S wing CL naught wing plus CL alpha wing alpha wing. Okay. Is alpha wing equal to alpha of the aeroplane? Hmm? Is what? Alpha wing here. This is the angle of attack seen by the wing airfoil, right? Okay. Is it equal to or not equal to the angle of attack of the aeroplane? If yes, why? If no, why?
It is not. It is not.
Why?
I'm not sure about this, but I'm pretty sure like the wing is placed at an angle, which is why it's the angle, the total angle is not equal to the.
Okay. What do you think about that? Do you agree or not?
I do.
You agree. Okay.
Is it is it because the wings are not positioned in the middle? They are either higher or lower, so that means it could have differences on that angle. For example, if you have a low wing, then the angle of attack might be higher than the angle of the wing might be higher than the angle of
And if you have a high
it
wing,
could be the opposite.
and if you have a center wing,
Then it could be same. Is what I'm thinking.
okay. So generally you agree about that they are not equal,
Yes.
but you are proposing a different reason.
Yeah.
Okay. Anybody else has a or different idea or agree?
Can be due to when you extend slabs. If you extend slabs,
If
if you extend the slabs or flaps on a.
the flaps, no, forget the flaps for now. Okay. The flaps change the whole airfoil. Okay, so we're talking about a different wing just by extending the flaps. So let's just ignore them for now. Hmm. Okay. As a matter of fact, I agree with the first point of view, okay, and disagree with the second. Okay. The thing is that if this is the reference line of the airplane, okay, I'm positioning my wing somewhere. Let's say I'm positioning it such that it lies on the axis. Okay? Still, if I draw the chord line of the wing, it may be parallel to XB, right? Or it may be not parallel to XB, right? So, generally speaking, yes, the setting of the wing relative to the rest of the body can force us to say that there is what we call induced, incidence angle. Okay? incidence, incidence, I'm not sure about the spelling, okay? Incidence angle of wing, okay? This incidence angle can be set to 0 by the designer or set to some other value. Because remember, for the wing, like we said last time, for the wing we don't have a choice. The reference line of the wing is the chord line, right? Okay, or for more general, the average chord line, right? But for the airplane, the reference line is a choice. Okay, it is kind of it makes a lot of sense to make it more or less parallel to the chord line of the wing. Okay, but more or less, yeah, more or less, not too much difference. Okay, but still, generally speaking, it may have an incidence angle, which is not related, just to answer the other point of view, it's not related to where the wing lies vertically relative to the axis. Maybe a high wing with zero incidence, okay? Or low wing with negative incidence. Got it? Okay, so the incidence angle is measured between the two lines, the chord line of the wing and the aeroplane reference line, or in other references usually called the fuselage reference line. Okay, I prefer the aeroplane reference line. Okay, now clear?
So like you said yesterday, right? Like you said yesterday, sometimes the horizontal stabilizer, they might change the incidence angle for stability.
Yeah,
So it's like that. Then
but for the wing, no.
yeah, not for the wing, but that's still a wing, right?
Yeah.
Horizontal stabilizer.
Mhm.
So in that case, the angle of attack for the horizontal stabilizer is different from the fuselage of the.
Yes, similar. Actually, now we are going to say also that the angle of attack of the tail doesn't have to be equal to the angle of attack of the airplane, right? Okay. So, yes, alpha wing is different from alpha, okay? And generally speaking, we will say that alpha wing is equal to alpha plus I wing, okay? Similarly, when we write the lift of the tail, we say Q infinity S tail CL tail, right? Wrong. I use every equation here to introduce something new. Okay? Not new, at least reminder. Okay? I left a space between Q infinity and S tail. Why did I do that? Yeah, because you have a very bad handwriting, so you're not really regular on how do you write, right? Maybe yes, but in this time, no. What happens? What's the difference? Come on, it's still Q infinity SCL, right? Why should the tail's lift be different from the wing's lift?
It's in the wake of the wing.
Okay.
It can, that's my answer.
Well, you're not on the wrong track. You're more or less on the right track.
So the purpose is for lifting.
Mhm.
The purpose is just for stabilizing, not to. It is there to be lifted.
It is a lifting surface, so it may produce lift or may not. So, generally speaking, it may produce lift, right? Mm-hmm. The induced angle of attack because of the wing. Okay, that will change the angle of attack, right? And the angle of attack appears in the equation in which part? In the CL, right? So we will come to that. Okay. Have you ever got the idea that the air as it flows over the wing, it slows down a little bit. Okay? So it approaches the tail with less dynamic pressure or less speed. You heard about that before? Okay? It's just like when you see an SUV running quickly on the sand. Why SUV and why sand? Because the SUV has a very bad aerodynamic profile, okay? And the sand visualizes the flow. Okay? If it's a Jaguar running on a smooth road, you wouldn't see anything but the same phenomena is going on. Okay? So what happens? You see the waves, right? But the air generally is basically a little bit moving with the car. Slower, but moving with the car. Okay? So when the car passes through the air, it gives it a little bit of speed forward. Hmm? Yeah, a little bit, right? That little bit reflects in an aeroplane in the other way around. As the whole aeroplane is flying, okay, if the wing sees the air flying at 100 meters per second, probably as it gets to the tail, it's 98 meters per second, 99 meters per second. Okay, a little bit slow. Okay, that's where we add the efficiency factor. Okay, this is usually between 0.95 and 0.99. Okay? So if you said that it's 1, the worst case scenario, you're introducing about a 5% error on the tail, right? Okay? And that's why in this particular analysis of today and probably next time, I'm going to use it 1. Later, we will not. But I'm trying to take you in a direction to explore the physics of the problem, not the real details of the problem. The details of the problem are not really hard, but I want to understand the concepts of what's going on. Okay? So, but it's there, right? Okay. So, L tail now is equal to Q infinity mu S tail, and then I will expand the CL tail, right? So it's CL naught tail plus CL alpha tail times alpha tail. Okay, that's what we did for the wing. Fair enough, right? Okay, and alpha tail is equal to what? Yeah, don't worry, minus 10,000 points anyway. If you say it right, minus 10,000 points. If you say it wrong, minus 10,000 points. So you have nothing to lose. If you don't say anything, it's minus 1,000,000 points. Hmm? Minus? That's it. So she got plus 500,000 points. I'm trying to create a deal between the central bank of UAE and my classroom in order to be able to transfer these points that I give or take from you into money. But the deal is falling apart every time I try, but eventually I will get it running. Okay. So for now, save the points. Okay. Until maybe you can exchange them in the open market someday. Okay. So what is epsilon? What is this angle that we are subtracting from the aerodynamic, sorry, from the angle of attack of the tail? Geometrically, okay, the tail is set at an incidence angle, right? So geometrically, we have the total angle of attack of the tail as alpha plus I full stop. Okay? Aerodynamically, something else is happening, which is the vortex, the downwash, right? The downwash is pushing the air down. Pushing the air down adds to the flow vector, okay? Which means that the tail sees the air coming at a different angle of attack. Not just because of its own lift. Remember that the tail is a small wing, right? So it has its own downwash. But now it's because of the presence of another lifting surface in front of it. Okay? That lifting surface is the wing. The downwash angle is a big deal. Okay? Uh, you probably heard about it before. Did you? Hmm? Yes or no? Okay? I know there are some gaps in this part. That's why I'm trying to fill it all. So if something you heard about before, fine. If not, tell me. Okay? So generally speaking, actually, epsilon is equal to some epsilon naught plus d epsilon by d alpha wing times alpha wing. I think it deserves a lot of tears, right? Okay? But partly lucky for you, for this lecture and the following one, I will deliberately, against all flight dynamics rules, ignore epsilon for 2 lectures. Only 2 lectures. Okay? So, epsilon is there. There is downwash, and it is significant. Not like what I said here about mu, right? Mu is large enough to be considered 1. Okay? But epsilon is not small enough to be ignored. Is that clear? Okay? But for the purpose of this lecture and the following one, I'll temporarily ignore it. Okay? So that no one would say, Mohammad Tawfik is teaching us wrong. Okay? No, I'm deliberately doing this for a purpose that I hope will be clearer for everyone in a small while, actually by tomorrow, by next lecture, inshallah. Okay? Okay? Okay. So, for now, ignore epsilon. Hey! Okay?
Doctor, may I ask what is that?
That's a smiling face, that's a crying face.
No, what is on top of the
It has that cone, the birthday
I
cone.
thought that was a tail.
Well, it can be a tail. It's a fictitious person. I'm not humiliating anyone real. I can humiliate my own drawing. Okay? Okay, so now at last we may write that the total lift of the aeroplane that's equal to Q infinity SCL is equal to Q infinity S wing CL wing plus Q infinity mu S tail CL tail. Right? Which gives us the first relation we were looking for is relating the total lift coefficient of the aeroplane to those of the lifting surfaces. Okay, dividing the whole equation by q infinity and then dividing by the reference area, which is by luck, by choice actually, okay, the wing surface area, right? Okay, so you end up with CL equals CL wing plus mu S tail over S wing CL tail. Okay, from this relation, we don't come up with a lot of conclusions. Probably only one, which is that most of the lift coefficient of the whole airplane is coming from the lift coefficient of the wing. Okay, which is not a surprise for any of us. We know that the wing is the main lifting surface, right? So affecting the aerodynamics, it should have the largest contribution. Okay?
Okay.
Okay. So far, so good. Let's now try to find those coefficients. We said that CL, usually as a linear relation, can be presented as CL naught plus CL alpha times alpha, right? Okay, so to find this, to get this relation, I need those two values, the slope and the y-intercept, right? To get the commonly known CL alpha relation, right? Okay, how to get that? We need to expand the CL of the wing and the CL of the tail in terms of the constants and the angle of attack, and collect all terms that are not related to alpha, okay? And consider them to be CL naught, the constant term, right? And all the other terms that are related to alpha will be collected in the slope term CL alpha, right? Okay, here we go. Let's write the CL of the wing, which is CL naught wing plus CL alpha wing times alpha wing, which is alpha plus I wing, right? Okay, and the other part is mu S tail over S wing multiplied by CL tail, which is CL naught tail plus CL alpha tail multiplied by alpha tail, which is alpha plus I tail minus ignore, right? We ignored that part. Okay, now what are the terms that are not affected by the angle of attack? Which well, actually most of them are not. This is not affected by the angle of attack. This is not affected by the angle of attack. So CL alpha wing, I wing is a constant number, right? And CL naught tail is not affected by the angle of attack. as well as CL alpha tail, I tail. Right? Okay. Now you can see why we ignored epsilon, at least for the moment. So now we can say that CL naught for the whole configuration is equal to CL naught wing plus CL alpha wing, I wing, plus mu S tail over S wing multiplied by CL naught tail plus CL alpha tail I tail. Is there anything that we missed?
The alpha?
Hmm?
It's alpha plus.
No, we're ignoring all the ones that
Yes, okay.
Actually, we didn't, as far as I see. Okay? So now we go for CL alpha of the whole aeroplane. Okay? Should be CL alpha wing plus mu S tail over S wing multiplied by CL alpha tail. Right? Okay. So what did we do here in this very simple exercise? And I consider it an exercise because basically this is not our objective. Okay? We're just trying to get familiar with all the notations. We said, okay, let's try to calculate the total lift and the lift coefficient of the whole aeroplane based on what we have or what we know about the wing and the tail. First, we said we will ignore the fuselage. We consider the fuselage lift not existing. Okay? Then we wrote the total lift as the summation of the two forces, lift of the wing and lift of the tail. That was quite straightforward. There wasn't much tricks here. Okay? Now, when we got to look for the coefficient, we said, okay, the coefficient is usually a linear relation between the angle of attack and alpha, and the angle of attack. The coefficient is usually a linear relation in the angle of the attack, Okay, so we can assume generally that it is a constant plus the slope times the angle of attack. Applying this to the coefficient of lift of the whole aeroplane and then applying it to the coefficient of lift of the wing, we realize that the angle of attack of the wing is different from the angle of attack of the whole aeroplane. Okay, that was good. Then when we went to the tail, we found that the same applies for the tail, but with two different points. The first is the air slows a little bit, which reduces the dynamic pressure, okay, of the air on the tail, and the effect of the downwash changes the angle of attack of the tail by a significant amount, which we called epsilon. Okay? So eventually we said alpha of the tail, the angle of attack of the tail, will be equal to the angle of attack of the whole airplane plus the incidence angle of the tail minus the downwash angle of the tail. Okay? And then let's keep it aside for a while. Now, putting everything together, okay, we were able to write down the total total lift coefficient of the aeroplane as uh, a summation, a weighted summation of the angle of attack of the, of the lift coefficient of the wing and that of the tail. Okay? Separating the constant parts and the parts that have alpha in them, we got finally a number, a constant that can present the y-intercept of the whole aeroplane, CL naught, in terms of few things related to the wing and the tail. Okay? And finally, we got the slope or the rate of change of lift coefficient with angle of attack of the whole aeroplane in terms of those of the wing and the tail. Okay, so this is the basic idea. This exercise is quite useful for the next step, which is we want to start investigating what's happening in the moment. Okay, the moment of the airplane is an important thing when we are talking about stability. When we try to analyze it, we will apply more or less the same process. Actually, in other literature, you will find it introduced in a different way, but stick to my way for now, in order to be able to, for me to be able to emphasize a few points that I want you to see. Okay? Okay. So, it's time to talk about stability then. Okay? What is stability? What would you call a stable body?
Which is not disturbed.
When?
A body which is not disturbed.
When it's not disturbed, it's stable.
A body that has a tendency to come back to the normal.
Okay? We all are under disturbance. Okay? All the time. Sometimes we feel the disturbance, sometimes we don't feel it, but it's there. Okay? For example, in seismology, which is something very far from what we do, okay? Seismologists, people who work with earthquakes, okay? They tell us that the crust of the earth is constantly vibrating. Okay, but the vibrations that are due to that we call earthquake are basically the vibrations, but with larger amplitude. So we're living in a continuous earthquake, right? But it's kind of not disrupting our lives. When the amplitude of it is large enough, then we feel disrupted. Okay? So again, stability doesn't mean that we are not under the effect of any disturbance. Rather, it means that when I am disturbed from my equilibrium, I tend to get back to my original setting or state. Okay? If you drive a car, most of us do, okay? If you drive a car and you take a turn, you don't need to turn the driving wheel back to its original position. Okay? That's a kind of stability. It's built in the design of the suspension. Okay? If you ride a bike, similarly, that happens. Okay? It has always the tendency to get back into its equilibrium. Okay? The direction. Okay? If you're sitting on an unwheeled chair, not like ours, and try to set yourself a little bit backwards. Okay? What happens when I remove my legs? I get back, right? Which means that this is a stable equilibrium. I'm intentionally pushing it to a different setting, but as soon as the force or the disturbance is removed, my body goes back, right? But what happens if I push too far? Then I'll fall on my back, right? You all want me to fall and die so that you get an A in the course, right? You will not. Okay, but what happened then? My equilibrium changed from what we call a stable equilibrium to an unstable equilibrium. Okay? The unstable equilibrium basically is an equilibrium. Theoretically speaking, we can put a cone on its tip standing, right? If there is a perfect alignment between the reaction of the table and the center of gravity or the direction of the weight, right? Then the cone should stay there. But why does it always fall down? It never stays there. Simply because a little bit of disturbance, which comes from the air, comes from the motion, the small vibrations that are all around us, a small change between an alignment between the reaction of the table and the weight, the direction of the weight, causes it to fall down. What's going on? All these are sending me.
But do not disturb.
Hmm?
But do not disturb. But do not disturb.
Put do not disturb? Okay, I will. I'm not used to using Teams. Okay? You will teach me how to use it.
Inshallah.
Please, inshallah. Okay? Uh, so, the very commonly used way to uh, explain stability is the ball in a bowl example. Okay? If the ball is on the concave side of a bowl, if you disturb it, it has a tendency to go back, right? If it's on the convex part of a bowl, if you disturb it, it will run away, right? Both starting positions are equilibrium, okay? Theoretically speaking, you can stay there forever. The differentiation between stable equilibrium and unstable equilibrium is when disturbance occurs. Okay? Actually, here there is a philosophical point of view. Okay? I will not impose it on you. I personally don't like to distinguish between what's called dynamic equilibrium and static equilibrium. Okay, but you will find it in a lot of literature all around you, so I will explain it to you. Okay, however, for me, equilibrium is equilibrium. Okay, static or dynamic is just equilibrium. Okay, usually what's referred to as dynamic stability or dynamic instability is related to vibration, okay, or a continuous change of state, okay. When the system is stable, what happens is that this continuous change of the state or vibration fades away, it dies out, okay. This fading is due to some kind of damping or control, something that absorbs some of the kinetic energy of the system, okay, to get it back to its original equilibrium. Okay, like a pendulum. When you start a pendulum, although it may take a long time, but eventually it will stop. Why did it stop? Because there is mechanical friction and aerodynamic friction that are absorbing energy from it all the time. Okay, what happens in a more complex system is that it may not have the tendency to go back to its original state, okay, while vibrating. So the vibrations may grow, okay. In this case, we call the system, whatever the system is, dynamically unstable. Okay? You vibrate, but the amplitude of the vibration is growing, then you are dynamically unstable. Okay? Or at least that's how they define. For me, as I told you, it's just unstable. Full stop. Dynamically or statically, it doesn't matter. Okay?
Okay.
Okay. There is always what they call neutral stability in dynamic and static conditions. Okay? Neutral stability means that the system doesn't have a tendency to do anything. It's just a zone. Okay? Put it on this side, it stays there. Move it to the other side, it stays there. If you get it to vibrate, it will continue vibrating forever. If you stop it from vibration, it will stay there forever. Okay? Which is basically a fictitious state. Okay? There is nothing in reality that's totally neutrally stable. There is always something there that will cause it to run away, either in a stable manner or an unstable manner. Okay? The value of knowing what's neutral stability, what neutral stability is in understanding that there is a barrier, a point at which the system switches from this side to that side. So you better not play around that barrier. Okay? Okay. Okay, now let's try to understand how does a horizontal stabilizer stabilize the aeroplane in longitudinal flight. Okay, just let's focus on the horizontal stabilizer. Now we are having two wings, a bigger one and a smaller one, but both are rigidly attached to what's called an aeroplane, right? And they are flying. Disturbance occurs all the time. Sometimes we notice it, sometimes we don't. Now, when some disturbance happens, say in the form of upward flow of the air, okay? So you're flying at a constant speed, but suddenly you get an uprising air at a speed of 30 meters per second. Huge amount. Okay? Air is blowing up. What will happen to the airplane? Right? So it makes sense. The whole airplane will go up. Right? Okay. Let's now turn our attention from the whole airplane to the two aerodynamic surfaces we have. What is going on with the wing? Okay? For the wing, as the air goes upwards, it adds to the incoming flow, means that the wing will see the air slightly tilted upwards, right? Slightly tilted upwards means that what happened to the angle of attack? The angle of attack is increasing, right? Clear? As the angle of attack increases, the lift increases, so it pushes the wing upward, which in turn pushes the whole aeroplane upward. Okay, good. Nothing new. We expected that, right? Okay. What happens with the tail? Well, the tail is another wing, isn't it? Okay. So now the tail back there is flying, air is flowing upwards, adds to the incoming air. Effectively the tail sees the air slightly tilted, increasing the angle of attack, so the lift on the wing will increase, pushing it upwards. In turn, it helps the wing in pushing the whole aeroplane upwards, right? But the tail is back there. Back there means that
That's generating more lift.
it creates a moment. When it creates more lift, it creates a moment around the center of mass of the aeroplane, right? This moment pushes the nose downwards, right? Pushing the nose downwards means that what happens mechanically, aerodynamics, yes, we saw it, it's clear, right? What happens is the lift increases on both wing and tail instantaneously, right? But as the lift increased on the tail, it creates a moment that wasn't there, okay? Pushing the nose downwards, decreasing the angle of attack of the wing, and decreasing the angle of attack of itself, right? Forcing the aeroplane to get back to where it was supposed to be. So, here is the scenario again. Air going up. First conclusion is the whole aeroplane is going up, which when we analyzed it is perfectly correct, right? Lift is increasing, so I'm accelerating upwards. But that was the first instant. Moment is a little bit delayed, okay? Because as the force of the lift on the tail increases, it pushes the nose downwards, or in more aerodynamic terms, it decreases the angle of attack of the aeroplane, the whole aeroplane, decreasing simultaneously, decreasing the angle of attack of the wing and the angle of attack of the tail, thus reducing lift again, which should push the aeroplane downwards, so that the airplane starts falling. When it falls, what happens? It's as if the air is pushing it down, right? When the air is pushing it down, what happens? Angle of attack decreases. Angle of attack decreases, right? Which means that the lift decreases on the wing and decreases on the tail. Okay? And because the tail is all the way back with some amount of mass with it, okay, it falls down, right, or creates negative lift, pushing the nose upward again. And we continue doing this, right? Okay? So, if you're lucky enough, okay, this jumping up and down will decrease with time, and you're back on track. If you are unlucky enough, it will increase, feeding one mode, feeding the other, right? Okay? Increasing the amplitude, and you end up falling down. Okay? Actually, before you fall down, all the passengers will start vomiting, and you will kill yourself before even you fall down. Okay? This is actually what we will call it later, the fugoid mode or the slow mode. Because of the being moved, being you get notice. I'm moving you. And actually, it's not even a conscious thing. You don't feel the motion. Your brain feels it. It's a small thing you don't feel being pushed around, okay? But because you have very sensitive balancing system, okay, it feels it. After a while, you start feeling nauseous, and you fall, and you start throwing up, okay? Some people have this all the time. Some people are better. Most of us are better in that case, but still, if it continues long enough, we'll all fall apart. We are not created for continuously being moved. Okay? Okay? So, now we understand the basic idea. This is how the horizontal stabilizer ensures, more or less, that the aeroplane is stable. Right? Okay. Let's turn that into some equations. Okay? Oh, it's already, we should finish by now, right? Okay. I know you love my lecture and you want me to continue forever. Okay? But for courtesy for other professors, okay, to find their students with them, okay, just give me a reminder at 15 minutes reminder, okay. Yeah, we have 90 minutes. Give me a 75-minute reminder, okay, so that I will see when to stop. Maybe I stop at that point or extend for very few minutes, but not just to go and forget myself. I usually forget myself. I'm used to 8-hour lectures, by the way. I can continue lecturing for a long time. But I think this is enough for today, alhamdulillah. And if you have any questions, I am here for.